tons of plastic waste enters our oceans each year, marine pollution has a variety of effects. It not only causes the death of many marine animals and plants, but also increases global warming and threatens humans indirectly and directly. Due to its large impact, it is important to save our oceans and keep them clean. Thus, the objective in our game is to deep clean the ocean. Our game begins with the start level that is playing. It introduces the environment, the aesthetic, and most importantly, the controls to the player. The introduction level ends with the giant trash bag showing the player what to look out for in the game. When this bag is destroyed, the player is teleported to the main game. During this game, the user controls a submarine that can fire torpedoes and trash to remove them. The submarine follows the mouse, meaning moving the mouse upwards would result in the same movement for the in-game object. This of course holds for all the other movement directions, including left, right and downwards. The up arrow key can be used to speed things up. The level of speed can be seen in the lower left corner. Pressing space directly fires the torpedoes from the submarine. The ocean environment includes the base terrain, corals and fish. If the player finishes its torpedo tank, the game is ended and the end scene is shown. But how does our game work? First of all, to keep things short, we are only discussing the main parts of the game and the things we think may set this game apart. Thus, things like the animation of the submarine and the torpedoes or the Blender modeling we did for some of the corals are not going to be discussed. Saying this, let's start with the main part of the underwater world. We used the Unity terrain object, which is handy because it has a height map which stores the height value of each vertex and thus makes it possible to gradually change those vertices. To get a realistic look, we used Perlin Noise for the height alteration. You can see the mockup here. As you can see, the alteration is scaled lower in the middle and higher at the outward bounds. We did this to guide our player through the game. We achieved this by using a parabola function to scale the noise vector at each vertex of the mesh. Additionally, you can see how each tile is created and the last one is destroyed. We did this for computational reasons. In the game it looks like this. When the player reaches a certain threshold, new tiles in the horizons are instantiated, while the old ones, which cannot be seen anymore, are destroyed. The plants and the fish are placed randomly. Speaking of fish, let's take a look at how they work. Each fish uses a raycast system to move around in the world. When the forward vector raycast detects an obstacle, it shoots out raycasts in different directions of the fish. Which way is the smoothest and smartest way to move towards? With this, the fish are able to move freely in the world. We used the system also to detect other fish. For the interaction between the fish, we employed the nature-inspired Boyd's algorithm. This Boyd's algorithm defines three main rules for the realistic movement in a flock of animals: cohesion, avoidance, and alignment. We applied weights to these rules to create a more dynamic and different moveset for each flock. Saying, if the alignment weight is high, the fish aim to swim in the same direction. However, if the avoidance one is high, they keep their distance to one another. In this sample environment, you can also see the glowing trash effect we did. We created this effect and all the other atmospheric effects in the game using shaders. The trash shader, for example, consists of a sinus time function and the Fresnel effect for the color overlay. Using properties of those shaders, we can change every aspect of the effect during runtime if we want to. Similar holds for the coloring effects of the corals. When trash is nearby, the color value is set to 0, making them appear sick. If the trash is destroyed, a coroutine is started, gradually increasing the color value and the glowing value. You can see the basis of that when changing the different values in the shader graph. Additionally, we used Perlin Noise and applied that to the normal map of those corals to make them look more detailed and interesting to look at. Again, this can be changed to our liking and also randomly to make each coral different to one another. This also holds for the color values of the corals, so that no two corals have the same color combo. This grants replayability and basically endless exploration of the environment.